I am Caleb. I'll be presenting what is normal, what is strange, and what is missing in a knowledge graph, unified characterization via inductive summarization. This is joint work with Xinyi Zheng, Vreeken, and my advisor, Danai Koutra. Knowledge graphs store general information about the world in the structure of a graph. For example, the fact that Anna Karenina was written by Leo Tolstoy. Knowledge graphs are constructed via mechanisms like crowdsourcing and web crawling. Due to the noise inherent in these processes, knowledge graphs contain errors. For example, the fact that Frankenstein, a book, published War and Peace, another book, is an erroneous fact. At the same time, there is missing information in knowledge graphs. For example, the author of Frankenstein might not be present in the knowledge graph. Moreover, these errors and missing information take many different forms. One example is entity confusion. For example, maybe the TV show Twin Peaks is confused with the location in San Francisco Twin Peaks. Another example is just blatantly incorrect facts, like a Boston Celtics player, Kemba Walker, playing for the Los Angeles Lakers. And beyond these, there are many other types of errors. Similarly, missing information can take different forms. One example would be a missing link, like the authorship link between Frankenstein and Mary Shelley might be missing. Another example might be worse, where even the entity is missing from the knowledge graph. And beyond these, it's possible that there are even types of errors and missing information that we don't even know about. The standard approach to dealing with errors and missing information is knowledge graph refinement, and this involves tailoring techniques towards each type of error or missing information. But this has a number of limitations. The first is the developmental time and cost involved in tailoring techniques towards each type of error and towards each type of missing information. The second is that it's impossible to tailor methods towards unknown types of errors. And how can we develop a method towards a type of error that we don't even know about? And the third is that if we want to run a suite of different tailored techniques on a knowledge graph, then that can be quite resource intensive, especially given that knowledge graphs are very large. And as knowledge graphs are completed, new facts are added to them, they only become larger, making this problem even worse. So in this work, we propose looking at the problem in a different way. Instead of tailoring techniques towards the particular details of one or another type of error, we want to know what is common across these different types of strange and missing things. And one thing they have in common is that they are all instances of abnormal things, and this is in contrast to things that are normal. So to place the problem, we have knowledge graphs, and we've pointed out that they have these problems, errors, and missing information. And the current solution to this is to tailor techniques towards each type of error or towards that missing information. But this has the problems that we talked about. The developmental cost is impossible to tailor techniques towards types of errors we don't even know about, and it's resource intensive to run all of these different methods on large knowledge graphs. So in this work, we're still given knowledge graphs, but instead of viewing these problems as distinct, we're going to view them as one problem, namely that of finding the abnormal things in the knowledge graph. And this allows us to flip the problem to inductive summarization. So summarization allows us to identify what is normal, and then everything that's not normal is abnormal. And we don't so much care about why it's abnormal, although we'll be able to reason about that. We just care that it's abnormal, because this is the common characteristic across all types of errors and missing information. We call our problem formulation knowledge graph inductive summarization, or KGIST for short. It states that if we're given a knowledge graph, which we'll call G, we would like to find a concise summary of that graph G, and we would like the summary to consist of inductive soft rules. These rules will then serve as our description or summary of what is normal. And it allows us to identify what is abnormal as the exceptions to the rules and the things that the rules leave unexplained. This has a number of contributions. First of all, by flipping the problem, we unify a number of different refinement tasks into something that's solvable with a single method. We also introduce a novel definition of rules, which are graph structural and expressive in nature. We introduce a minimum description length-based approach, which ensures a concise set of rules, allowing KGIST to efficiently refine large knowledge graphs. In the coming slides, we will introduce a number of things. The first will be some preliminary definitions. After that, we will introduce our minimum description length-based problem formulation, and we will then introduce a method to solve that problem. The output of that method will be a summary or description of what is normal in the knowledge graph, so we will then show how to use that summary to identify what is abnormal or anomalous. And the last thing we'll show are some experiments evaluating all of these parts. A knowledge graph in this work is treated as a labeled and directed graph. As a graph, it consists of edges, or sometimes called triples, and these consist of a subject node, a predicate or relationship, and an object node. We can represent this mathematically as an adjacency tensor, where each slice of the tensor corresponds to a particular relationship type. For example, the first slice might capture the written by relationship type, in which case it captures all of the things that are written by people. In addition to this binary adjacency tensor, we also have a binary label matrix. This specifies the labels on each entity. For example, the fact that Anna Karenina is a book. We introduce a new graph-theoretic formulation of rules, defining them recursively as rooted, directed, and labeled graphs. A rule asserts things about the nodes with the root labels L sub g for the rule g. For example, the rule on the right applies to books, and it asserts things about them. Specifically, two things. It asserts that they have fictional family characters and that they are written by authors who are born in countries. The first thing it asserts is its first child. And because the rule is recursively defined, this child is itself a rule. It applies to all fictional families, but because there's no other component of this to the rule, it doesn't assert anything about them, so it has an empty child set. The second child of the book rule applies to authors, and it states that they're born in countries. And again, because this is recursively defined, the country node is itself a rule, asserting things about countries, but it just so happens that it asserts nothing, so again it has an empty child set. When a rule asserts things about a particular node, it induces a subgraph around that node. For example, the rule that we described in the last slide applies, among other things, to War and Peace, a book. It asserts that it should have some fictional family characters, and in this case, these are the 5 characters it has. It also asserts that it should be written by an author, in this case it's Leo Tolstoy, and that author should be born in a country, in this case, Russia. So this induces a subgraph, and it does so by following the guided traversal implied by the rule. The set of all these traversals are called the rule's correct assertions. However, the rule may not correctly apply to all book nodes. For example, a non-fictional book like Syntactic Structures, since it's non-fictional, doesn't have any fictional family characters. As a result, the rule asserts something about it that's not true for this node, so we call this an exception to the rule. Another way of thinking about it is a failed guided traversal. The total set of things that the rule asserts are the things that it correctly asserts, plus the exceptions to the rule. The minimum description length principle is an information theoretic formulation of Occam's razor. It states that if we're given some data, which we'll call D, we would like to find a model M describing that data, and we would like the model that minimizes the description length. And the description length breaks down into 2 components. The first is the number of bits that we need to describe the model M, and the second is the number of bits that, given that model M, which describes the data, how many bits we need to describe the data. This has a key advantage. Because we're trying to minimize the number of bits, it encourages conciseness, which leads to a smaller model, which makes it then easier to use our model to refine large knowledge graphs. There are 4 steps involved in this. The first is to define what a model is, or to define the model space. The second step then is to derive or define the description length for the model, and also the description length for the data under the model. And the 4th step is to select a model from the model space, namely the one that minimizes, or at least approximately minimizes, the description length. So we can reformulate our problem now in terms of the minimum description length principle. Given a knowledge graph G, we would like to find the concise set of inductive rules M that minimizes the description length. If M here is our set of rules, then these serve to describe what is normal. This is our summary of what is normal in the knowledge graph. And then the expensive parts of the description length will reveal what is abnormal, and it'll do so in an information theoretic way. Next, we will show how to formulate our problem in terms of the minimum description length principle in more detail. The first step, again, is to define what a model is. and we will define it quite simply as just a set of rules, each of which has correct assertions, just like we saw before. These correct assertions serve to describe the structure of the graph, first of all, because again, it's a guided traversal, which induces a particular subgraph. So the edges of that induced subgraph have been described by the rule. It also describes some of the semantics of the graph because it reveals the labels in the induced subgraph. For example, the fact that Leo Tolstoy is an author. The second step is to derive the description length. And to do so, we're going to take description quite literally and imagine that we are describing the knowledge graph to somebody else. So imagine that Alice has a knowledge graph and Bob would like to know about it. So Alice is going to describe the knowledge graph to Bob, and we'll use this scenario to think about what components Alice needs to describe to Bob in order for him to know about the knowledge graph. So Alice is going to send 3 pieces of information. She'll first send some model-independent information, and this will have a constant cost, but we don't care about it for the context of model selection because it's model-independent. It's only dependent on the data. She will then send a model, and the model will serve to describe parts of the knowledge graph, but it might leave some stuff out, in which case it makes some error. So the last thing she'll do is send along any error explicitly that the model might make. And Bob just requests that she send this information as concisely as possible. The first thing that Alice will send is the model-independent information. So this can be things like the number of nodes in the graph, the number of edges, and the node IDs, things that won't change regardless of what model we select. So once she sends this information, Bob just has a big bag of entities, and he doesn't really know what they are or how they link together. So the next thing that Alice will send along is a model describing this knowledge graph. And a model, again, is a set of rules, so the first thing that Alice needs to tell Bob in order for him to know about this model is how many rules are there in the model. And we'll assume for simplicity of this example that there's just one rule in the model. Of course, in general, it's going to be a lot more than that. But she sends this one rule, and she just basically has to describe what the rule looks like. At this point, Bob knows the rule applies to books, so he can start looking at books. But then a problem arises. Bob finds the first book, let's say War and Peace, and he knows that the rule asserts that War and Peace should have fictional family characters and it should be written by an author, but he doesn't know who the characters are and he doesn't know who the author is. So Alice needs to send this information along. Essentially, she needs to give some more information along the way as he traverses the graph from War and Peace. So she will do this send this extra information, first sending the characters for War and Peace, and then the author, and then the author's birthplace. And at this point, Bob has this particular part of the knowledge graph inferred. He moves on to the next book, which is syntactic structures. But recall this is a nonfiction book and doesn't have any fictional family characters. So when Bob goes to find those fictional family characters, he's not going to find any. So Alice needs to tell Bob, this rule applies to books, but don't apply to syntactic structures because it's an exception. So she'll point out all of these exceptions. And at this point, some of the graph has been filled in by this very simple model, but some of the nodes aren't linked into the graph yet. And because the graph is represented by a binary label matrix and a binary adjacency tensor, we can imagine that Bob has essentially filled in some of the ones in that matrix and tensor, and Alice just now needs to fill in explicitly where the remaining ones are. So she'll first fill in the ones in the label matrix, which reveals the labels, and then she'll fill in the ones in the adjacency tensor, which reveals the missing links. And there you go. Bob has the knowledge graph. These are the different components that go into the description length, which allow us to evaluate the quality of a model. With this formulation in hand, the next step is to derive a method for finding such a model. A model is a set of rules, so we can then imagine the set of all possible rules, or a set of candidate rules, and any subset of this set of candidate rules is a valid model. But the problem is that there's an exponential number of these. So to avoid enumerating or searching an exponential space of models, we'll instead start with simple candidate rules. Simple meaning they assert only one thing, and compose those into more complicated and expressive ones. So the first step is to generate these candidate rules. And we'll do this by iterating over the graph, and each time we encounter an edge, we will generate rules to explain it. So for example, if we encounter a person who performs music, then we'll generate that rule describing that schematic structure. So we might also then generate books are written by authors, cities manufacture cars, and mountains are located in places. The next step then is to rank the rules for consideration in the model, and we'll do so by measuring how much they compress the graph. So once we've computed this compression value, we will rank them based off of how much compression they achieve, and consider them for inclusion in the model in this order. As we consider these rules one at a time for inclusion in the model, if the description length goes down by adding the rule, then we'll keep it. If the description length goes up, however, we'll throw it out. So at this point, we found an initial model. But remember that these are just simple rules that only assert one thing. And we'd like to make these more expressive, so we will introduce two refinement steps. The first is a merging refinement, so it merges rules. And I'll demonstrate by an example. If we have books are written by authors and books are published by publishers, then we can state this more concisely as one rule. The second refinement is a nesting refinement, and this nests recursively different rules. So for example, if we have the rule that mountains are located in places and the rule that places contain hiking trails, the second rule is not very accurate because, again, there's a lot of places that don't contain hiking trails, like buildings, for example. So we can make this more accurate by nesting it underneath the initial rule. So now it only applies to places that are the locations of mountains. And naturally, those are a lot more likely to contain hiking trails, making this rule more accurate. After these two steps, we've refined the model to contain more expressive rules. The next step, then, is to use this summary or description of what is normal in the graph to identify anomalies in an information theoretic way. We'll first derive an anomaly score for nodes. The intuition is that nodes that violate a lot of rules are likely to be anomalous. We can capture this in information theoretic terms by adding up the number of bits that Alice spent pointing out that node as an exception to rules when describing the graph to Bob. To identify anomalous edges, we would like to capture the following two intuitions. The first is that edges that are not explained by the model, in other words, things that Alice had to describe to Bob explicitly, are likely to be anomalous. And furthermore, edges that have anomalous node endpoints are likely to be anomalous. So we can capture the first component by computing the number of bits that Alice spent describing all of the unexplained edges and then dividing that across these unexplained edges. And we can capture the second component by just adding in the anomaly scores for the entities that we computed in the last slide. So the next step is to evaluate our method. And we do so with a number of research questions. The first is whether KGIST characterizes what is normal. Does it identify what is strange and missing? And does it do all of this in a scalable way? And we will evaluate these questions on three real-world knowledge graphs, NEL, DBpedia, and Yago. Our first question, whether KGIST finds what is normal, we first ask as, does KGIST compress real knowledge graphs? Because if it's able to compress them, then that means that it's characterizing what is normal in the knowledge graph. Our first knowledge graph, NEL, requires 6.2 million bits to describe using no model at all. In other words, no rules at all. Using the model that KGIST mines, it only requires 63.57% of those bits. But it's hard to tell whether that's a good number or not, so we compared to a baseline, which instead of using the minimum description length principle to select a model, instead just selects the rules that apply most frequently or have the highest support. It actually leads to an increase in number of bits in the description length. On DBpedia, it requires 119 million bits to describe with no model, and KGIST compresses this down to 69.77% of those bits. In contrast, again, the baseline requires multiple times more bits. And again, on Yago, it's a similar story. It requires 793 million bits to describe with no model, and with KGIST, we're able to compress that down by 74.04% of those bits. And the baseline, again, requires many more bits. The second question is whether the rule set that KGIST mines to compress the knowledge graph is concise. To answer this question, we compare to AMY, which is an existing rule mining method that doesn't use the minimum description length principle and instead uses the support and confidence framework of associational mining. On NEL, KGIST mines 573 rules, and in comparison, AMY mines a whopping 32,676 rules. Similarly, on DBpedia, KGIST mines only 498 rules, while AMY mines 6,963 rules. So in both cases, KGIST is mining orders of magnitude fewer rules than existing rule mining techniques. Another question is whether the rules that KGIST mines in this concise set are human readable. And we demonstrate that they are with a couple of examples. The first one reads that political offices are held by politicians who endorse and are endorsed by other politicians. And the second one reads that countries contain cities, and cities are the locations of buildings. Our second research question is whether KGIST finds what is strange in the knowledge graph. To evaluate this, we compare to a number of baselines. Some of them are supervised embedding methods, complex and trans-Z, and some are unsupervised. SDValidate is a statistical-based method, AMY is the same rule mining method we used in the last experiment, and KGIST frequency is similar to the procedure we used before, where we select the most frequent rules, the rules with the highest support, but then we use our information theoretic anomaly scores to find anomalies, and KGIST is our method. We inject ground truth anomalies and evaluate how accurately we can identify them. And we inject 4 different types of anomalies to show that we can find many different types of anomalies with a single method. For each of these 4 types of anomalies, we select Q% of all nodes, and we perform a certain perturbation. The first is that we remove a label, the second is that we add a label, the third is that we inject 1 or 2 edges at random adjacent to the node, and the fourth is that we replace a label. In each of these cases, we consider the adjacent edges as perturbed, and these are the ground truth that we use to evaluate the accuracy. Across all anomaly types, KGIST outperforms all baselines by a statistically significant amount, and we give the upper bound recall in F1 to show why these numbers appear to be low. It's just because there are many more errors injected than 100, so the maximum achievable at 100 is quite small. Not only can we accurately identify anomalies, but we can also reason about why something is anomalous. For example, the node Pennsylvania in NEL was identified as anomalous, in part because it was an exception to the rule that states are the headquarters of sports teams. So in NEL, Pennsylvania didn't have any sports teams listed, which is false, or it's missing information, because Pennsylvania has plenty of sports teams, like the Pittsburgh Steelers and the Philadelphia Eagles. Our third research question is whether KGIST finds what is missing in a knowledge graph. To evaluate this, we remove some of the nodes in the graph. For example, perhaps we remove Mary Shelley. We then run KGIST on this perturbed graph, which results in a model, a set of rules. And we apply these rules to find the exceptions that point out where entities are missing. So if we identify that Frankenstein is missing an author, then that's considered a true positive. Our task is complementary to link prediction because link prediction assumes that both entities are in the knowledge graph, while we assume that one of the entities is missing, which is why we don't evaluate against link prediction methods. We evaluate against AMY plus C, which is an extension of AMY designed for measuring the completeness of knowledge graphs. We also evaluate against frequency, which again just selects the most frequent rules. And across multiple data sets, KGIST statistically significantly outperforms the baselines at identifying where entities are missing. Our final research question is whether KGIST is scalable, and running it on 3 different graphs, we observe that KGIST is near linear in the number of edges. In conclusion, in order to address the errors and missing information prevalent in knowledge graphs, we introduce a unified solution, knowledge graph inductive summarization, and this finds what is normal, strange, and missing in a knowledge graph. By reformulating the problem in this way, we're able to unify multiple refinement tasks, all solvable with KGIST. We also introduce expressive graph theoretic rules, which allow many types of errors to be found, And we introduced the use of the minimum description length principle into knowledge graph rule mining in order to ensure a concise rule set. This helps alleviate some of the resource challenges of knowledge graph refinement. Thanks so much for watching this presentation.